Stanford University.
Most of the basic ideas that we're going to talk about this quarter originated out of questions having to do with renormalization, puzzles, and sometimes puzzles, sometimes useful observations about the renormalization of the standard model. So I thought it would be a good idea to spend a little bit of time explaining to you. We've done this before. We've done this a couple of times. But still, to describe what renormalization is. It's a combination of two things. It's the combination of learning how to eliminate out of the description of physics things having to do with distances which are so small that they're irrelevant to the questions that you're asking. And it is all, the other half of it is very simple. It's dimensional analysis. In fact, it's learning to think about how dimensional analysis tells you the answer to some of the very difficult problems of quantum field theory that have to do with distances much, much smaller than you might be interested in. Here's some simple examples of renormalization, namely getting rid of things which are too small to be interesting to you. If you're interested in the nucleus and how the nucleus works, you may begin with quarks. Quarks are the fundamental underlying constituents of the nucleus. But for many, many purposes, the nucleus is really a collection of protons and neutrons, and it doesn't matter very much what those protons and neutrons are made out of. So a simple step is to solve the theory of quantum chromodynamics to discover and to compute the properties of the protons and neutrons. But then once you're finished with that, well, in computing the properties of the protons and neutrons, you might mean their mass, you might mean their spin, a few other properties, but also the forces between them. Also the forces between them. In a nucleus, the protons and neutrons move pretty slowly. So there's no real need or no strong need for relativity theory. Basically, the nucleus is, roughly speaking, described by the non-relativistic quantum mechanics of protons and neutrons. And all you really need from the quark theory is to find out what the properties of protons and neutrons are, masses, spins, and the forces between them. Once you've got that, you can forget where it came from and say protons, neutrons, and some simple forces between them. But then if you're interested in atoms, you may not be terribly interested in what makes up the nucleus. You use nuclear physics to calculate the properties of nuclei. Which nuclei exist, which nuclei, what they're. In fact, if you're interested in atomic physics, you're not even very interested in the mass of the nucleus. But still, you might want to know the mass of a given nucleus, a few of its properties, not much, basically just its mass and its charge. Once you have the mass and the charge of the nucleus, you can forget completely where it came from. You can forget protons and neutrons, and you can say there are nuclei. There are 92 of them. Well, more than 92 because there are isotopes. But you can start over again and say the elementary particles for today's thoughts, not today's, but I mean if you were doing nuclear physics, if you're doing atomic physics, you would say we start over again with a new set of elementary particles. We forget quarks, we forget protons and neutrons, and we start with nuclei. 92 of them, or however many of them there are, plus, of course, electrons. Electrons are pretty small, but we can't get rid of the electrons and still be able to do atomic physics. So we calculate the properties of atoms. Atoms mean nuclei plus electrons. We calculate their properties, and once we have their properties, we can say, all right, here's the collection of atoms that exist in nature. There's cookie atoms and coffee atoms and chocolate atoms, ketchup atoms, all those various kinds of atoms. And once you have them, you don't need to ask where they came from anymore. Well, you might want to know a little bit more than that, because if you have to calculate, we're going to talk a little bit about the properties of, we're not going to talk about the properties of molecules tonight, but we're going to talk about how you think about molecules, how you go from atoms to molecules. But in going from atoms and molecules, it's the same kind of deal. You figure out how atoms build themselves into molecules, and once you have molecules, you can more or less forget where they came from and start putting them together in tinker toy assemblies and build up anything from there. So at each stage, you eliminated the things which were smaller than you were really interested in. And the result was a more coarse-grained description, perhaps not as exact a description, but a far more useful description for your purposes. Well, the same thing is true in quantum field theory, where you have things at all possible scales. Every possible wavelength constitutes a degree of freedom, waves of arbitrary wavelength, arbitrarily small wavelengths. But in describing physics at one length scale, you don't really want to have to deal with all the things at very, very small length scales which are uninteresting to you. So you invent a way of summing up all of the effects of very small distances and replacing it by effective new parameters in your description. That's all that renormalization really is. That together with some dimensional analysis. Let me give you an example of renormalization. Again, it's just this example of going from atoms to molecules, or from going from nuclei plus electrons to atoms, and how you deal with atomic forces and so forth, where atomic forces come from, how they come out of electrons, protons, not protons and neutrons, but nuclei and electrons. This is a classic example. It's not usually thought of as renormalization, but it is renormalization, where getting rid of the very small degrees of freedom and also the very fast degrees of freedom. Small usually goes with fast. The smaller a system is, typically the faster its motion is. So you're getting rid of not only small things, but also very rapid things. That's the goal of renormalization. So let's start with something we know very well, the theory of atoms. The theory of atoms is very simple. It's just a nucleus and a bunch of electrons. And what I'm actually interested in is a pair of atoms. It could be a pair of hydrogen atoms, but that could be more complicated than a pair of hydrogen atoms, just some pair of atoms. And what I'm interested in is describing the dynamics of this pair of atoms in a simpler way than the complex structure of electrons, a cloud of electrons, and all that very, very complicated stuff. What I'd like to describe them by is simply two particles that I call atoms with forces between them. How do you understand those forces? Now, the advantage that you have here, which is an advantage, is that the electron motions are very, very fast by comparison with the motions of the nuclei. Nuclei are heavy. Nuclei are 1,000 times or 2,000 times, and the lightest nucleus, the hydrogen nucleus, is 2,000 times heavier than an electron, and bigger nuclei are even more massive. So you can almost think of the atom as a heavy bowling ball with a bunch of little flies surrounding it, and the flies moving very, very much faster than the bowling ball is going to move, because a given force is just not going to accelerate the bowling ball very much. So you can make an approximation, and in your first approximation, you say that the bowling ball nuclei are so heavy that they don't move at all. What I want to calculate is the effective potential, the potential energy between two nuclei, or between two atoms, in a way that gets rid of the electrons. in fact, which gets rid of separately the electrons and the nuclei. So what do? You start, this is a quantum mechanical problem, and as any quantum mechanical problem, you start with a Hamiltonian. The Hamiltonian is just another expression for the quantum mechanical version of energy. So let me write down for you what Hamiltonian I would write down if I really wanted to do this problem. I would say, first of all, I'm not interested in corrections coming from the special theory of relativity, from relativity theory. That's not interesting for molecules. So you begin with non-relativistic quantum mechanics. And that means the energy, first of all, consists of the kinetic energy of the nuclei. Let's take the two nuclei to be the same. It could be, for example, hydrogen. All right, so the momentum of the first nucleus is, let's call P1. P1 squared divided by twice the mass of the nucleus. That's the kinetic energy of the first nucleus, just the nucleus, not the atom. Then plus P2 squared. That's the kinetic energy of the second nucleus. And then, of course, there is the Coulomb force between the nuclei. The Coulomb force between the nuclei is plus E squared. In the energy, it's plus E squared divided by the distance between them, R12. Let's just call it R12. That's the, and I've left out dimensional 4 pi's and stuff like that. That's not what I'm interested in. And then what comes next? The electrons. So let's sum up everything that goes into the electrons, everything that involves the electrons. First of all is the kinetic energy of all the electrons. Okay? So let's call the electrons, call the momenta of the electrons Q. Q sub I squared over twice the mass of an electron. Let's call that small mass. Here's big mass for the nucleus, here's small mass for the electrons, and this is a sum over all the electrons. Sum over all the electrons, that's there, that's their kinetic energy. Then there's the forces between the electrons, that's plus E squared divided by, let's call it little r ij. That's the distance between the ith and the jth electron. This is the Coulomb energy between them, electrostatic energy. And what have I left out? I have left out the force between the protons and the electrons. So that's one more term. I guess we can call it minus E squared because they're opposite charge, attractive, minus E squared divided by the distance between the ith electron and either one of the nucleus. I don't know what to call it. Let's call it capital R 1I. That means the distance between the first nucleus and the ith electron, and then another one for the second electron, R sub R2I. All right. There are things which involve the electrons, and there are things which involve the nucleus. Here are all the things that involve the electrons. Now, intuitively, and I won't try to prove this, intuitively, there are two time scales here. One time scale is long, and it has to do with the very slow motions of the nuclei. Why are the motions of the nuclei slow? Because the nuclei are very heavy, and they move around under modest forces, in fact. They're never accelerated very much inside a molecule, and so we think of them as very, very slow by comparison with the very, very rapid motions of the electrons. Electrons, much more rapid than the... So the electrons form a blur, and we're trying to get rid of that blur or replace it by something else. Well, this is fairly easy to do, in principle, in concept. To actually do it might be more difficult, but in concept it's very simple. You take everything in the Hamiltonian here that involves the electrons, group it together, and think of it as the Hamiltonian of the electrons alone. But what about the positions of the nuclei? For present purposes now, we're going to say the nuclei move so slow, and the electrons adjust their wave function so rapidly that in first approximation we can say the nuclei are not moving at all. They're fixed, they're nailed down, they're stationary, and we just fix them, and we think of this as a Hamiltonian for the electrons in a fixed background, the fixed background being the nailed down stationary nuclei. So we fix the positions of the nuclei. Once the positions of the nuclei are fixed, then this becomes the expression for the energy or for the Hamiltonian, but it's still a function of the position of the nuclei. It's a function of the position of the nuclei, but those can just be, yeah.
You set the momentum to zero?
Well, whose momentum?
The proton.
For the moment, yes. In fact, for the moment, we don't even need to, we just say they're nailed down, they're very, very heavy. Okay? We're not going to violate the uncertainty principle or anything like that, because eventually we're going to take those momenta back into account. And the approximation here is just that they move slowly. All right, then we take this Hamiltonian, which only involves the electron coordinates and the fixed positions of the nuclei, and we solve it. What does that mean? We solve the Schrodinger equation, and we solve the Schrodinger equation for the lowest energy state. We find the lowest energy state, and in fact, more important, the lowest energy eigenvalue, the energy, the ground state energy, basically the ground state energy of the electrons in the background of the nuclei. Let's call that something. Let's call that, let's see, let's just call it E. E of electrons. All the terms that involve electrons. E of electrons. And what is it a function of? The only thing it's a function of is the positions of the nuclei. That's all. Everything else is taken care of. This is the lowest energy state, the lowest energy associated with the positions of R1 and R2. Those are the positions of the nuclei. Now what do we do next? Now we say, okay, let's take all of this and forget about it, erase it. We can't forget about it, of course, not completely. But we can replace it by the energy of the electrons as a function of R1 and R2. That's plus E of electrons of R1 and R2. What do we have now? Now we have a problem involving only the protons, or only the nuclei, excuse me, only the nuclei, a potential energy between them that was originally there, plus another term in the energy which also can be regarded as potential energy. It's a function of the position of the two nuclei, and therefore it's a contribution to the potential energy. This is the way that we eliminate out of the problem the electrons and replace it with something else. In fact, it's only a function of the distance between the electrons. And so what we actually find is that the entire dynamics of the electrons is summarized. We first of all have the Coulomb potential between the nuclei, but then another term in the potential energy and the other term in the potential energy. When you combine it with this term here, gives you a force, or gives you a potential energy which looks something like this. When the nuclei are extremely close together, it's completely dominated by the Coulomb term here, repulsive. When they're far away, there isn't much energy between them, and in between there's some attraction, and that attraction is due to the electrons. However, we never have to think about the electrons again. For this hydrogen molecule, or whatever it is, we don't have to think about it. We just have an effective potential between them, and we solve the problem of two protons in a potential like that. We know what the solution is going to look like. It's going to sit at the bottom here. It's going to be some wave function. And that's a process of, number one, eliminating fast degrees of freedom, but we can also call it renormalization. We started with a potential which was just this potential. We got rid of the high frequency degrees of freedom, and the entire potential energy was then replaced by another function. So the potential was renormalized. That's the basic idea. All renormalization is associated with that idea. eliminating very, very fast degrees of freedom and replacing them by an effective, slow, renormalized Hamiltonian, or however you're doing your dynamics. Okay, so that's renormalization. We want to apply that to quantum field theory. So I'm going to show you how you apply that to quantum field theory. What is it that you get rid of? What you get rid of, you can either think of it as things associated with very small distances, or you can think of it as things having to do with either very high frequencies or very, very short wavelengths. Short wavelengths entail high frequencies, and so the things that we're getting rid of in the problem are the degrees of freedom associated with very high energies, very high frequencies. Let's see. Yeah, before we do that, let's just go through some dimensional analysis, some very simple dimensional analysis. Just to take a break from renormalization theory for a minute, and I just want to do some simple dimensional analysis. First of all, in physics in general, there are three length scales that you need: distance, time, and mass. And we can get rid of two of them in elementary particle physics by taking the two-dimensional parameters of elementary particle physics, namely h bar and c, and setting them equal to 1. That's a specification of two combinations of the scales in the problem, of the dimensions in the scale in the problem. But it still leaves one dimension that you have to specify, one dimension that you need, one quantity with dimensions, and that dimension can be taken to be a length scale. Right? Once you set h bar equal to 1 and c equal to 1, there's only one dimensional quantity that has to be specified. It can be taken to be a mass, it can be taken to be an energy, it can be taken to be a momentum, or it can be taken to be a length, or it can be taken to be a time, but you need one specification. All right, with these notations here, then the units of mass, the bracket means the units of mass, are the same as the units of energy. Why? Because E equals mc squared and c is equal to 1, and also equal to the units of momentum. Also true that the units of length, what should we call that? Length are the same as the units of time. That's because c is equal to 1. But the units of length and time are not the same as the units of length of mass and energy. In fact, they are inverse. So, one-dimensional specification, either a unit of mass, length, or time, but once you fix it, that's it. And all masses have units of inverse length, all momenta have units of inverse length, and so forth. So let's keep that in mind, first of all. That's a bit of dimensional analysis. We have only units of length. Everything else is determined, or mass, depending on how we think of that. Okay, let's now talk about a typical quantum field theory. Let's see, I think we'll start with a scalar quantum field theory, and I'll show you what's entailed in renormalization. We have, for simplicity now, just a quantum field theory with a single scalar field, phi. That's all there is. It has a Lagrangian, and from the Lagrangian, we derive Feynman diagrams. We're going to talk about those Feynman diagrams a little bit, and even set up roughly what a calculation of a Feynman diagram would look like, some simple ones. Okay, so there's a Lagrangian. Here is the Lagrangian for phi. It's very simple. It's just the derivative of phi with respect to either space or time squared. We've done these things before. That's the kinetic term in the Lagrangian. And then there may be a potential energy in the Lagrangian, minus v of phi, which is a function of phi. Now, what are the units of a Lagrangian? The units of a Lagrangian Okay. What do we do with a Lagrangian? We integrate it over, we use a Lagrangian in the principle of least action. That's what a Lagrangian is for. It's whole, in classical physics in any case. In quantum physics, it's used in the path integral. But basically, in either case, the quantity of real interest is the action itself. And what is the action in terms of the Lagrangian? It's the integral of the Lagrangian. But the integral of Lagrangian over what? And space. Time and space. This is the Lagrangian of a field theory. So the interesting quantity, which is usually called S, sometimes action, sometimes I, it doesn't matter, but for now it's S for action. Huh? S for sex. That's like action, isn't it? No, I didn't say that. All right, S for action, and that's the integral d4x of the Lagrangian. And the action is always something, yeah, question. Action has units of h bar. But h bar has been set equal to 1. So h bar is now dimensionless. Action is dimensionless. Has no dimensions at all. And that means whatever the Lagrangian is, it must have inverse length to the 4th power. The Lagrangian must have inverse length to the 4th power, the Lagrangian density in here. Must have inverse length to the 4th power. Now, what I'm really after is the dimensions of the field itself, phi. What is the dimension of phi itself? So let's see if we can figure it out. The Lagrangian has to be, let's take this term here. This term here is derivative of phi with respect to x squared, and it has to have dimensions of inverse length to the 4th. Inverse length to the 4th because it has to cancel this d4x here. d4x, or x, has units of length. This must have units of length to the minus 4. Okay? Well, whatever the units of phi are, the units of the derivative of phi are the units of phi times length to the minus 1. That's the unit of the derivative of phi. Differentiating with respect to x just gives you a length inverse. And now the square of this is just the dimension of phi squared times length to the minus 2, and that has to give you length to the minus 4. And that tells you that the units of phi squared must be length to the minus 2. Or, to summarize, the units of a scalar field, are just inverse length, length to the minus 1. Good thing to keep in mind. Very, very useful for all kinds of purposes. That's an example of using some simple dimensional analysis. Now, what about the rules for Feynman graphs? Let's talk about the rules for Feynman graphs a little bit. First of all, the Feynman graphs all come from V of phi. V of phi might have things like in it. What does it have in it? V of phi has things in it like m squared over 2. That's just a parameter. It really is, of course, secretly the square of the mass of the field divided by 2 times phi squared. And then it can have things involving, let's call it g times phi cubed. And then it can have things with phi fourth in it. Let's call the coefficient of phi fourth lambda. That's a traditional notation, lambda phi fourth, and on and on and on. It can have all kinds of terms in it. And notice that these terms also have dimensions. These terms also have dimensions. In fact, the phi squared has units of length to the minus 2. Phi cubed has units of length to the minus 3, and so forth and so on. And from that, we can read off what the dimensions of V of phi are. Okay. Now, let's talk about Feynman diagrams. Feynman diagrams are built out of vertices, and the vertices come from the potential here.
Is G units of mass?
G, let's see. So, yeah, G must have a unit of mass, yeah. Why is it mass? The whole thing has to have units of length to the -4. All right, here's length to the -3. This must be inverse length, but inverse length is the same as mass. Right. So G would have units of mass. This obviously has units of mass squared. What about the dimensions of lambda? Dimensionless. No dimensions at all. That's significant. Dimensionless coupling constants are especially important in renormalization theory. The other ones have units of either mass, mass squared, and of course if you introduce more terms up here, then you can follow what the dimensions are. Okay, now a quantum field theory, or the rules of Feynman diagrams, are built out of two elements. One element are the vertices, and the vertices are read off from the potential here. For example, G5 cubed represents a vertex in which 3 particles come together. And the coefficient of such a vertex in a Feynman diagram is just G. Right? Phi to the 4th, that's 4 particles coming together. This one has coefficient G. This one has coefficient lambda. Right? What about m phi squared? Well, m phi squared is a very simple thing. A particle comes in, let's put a little cross to indicate, and goes back out. I put a little cross there just to indicate that, that something happened there, namely the particle was absorbed and re-emitted, and the coefficient is just m squared over 2. So when you're building a Feynman diagram has a value. The value corresponds to the amplitude for a process to happen. All right, it has a value, and in building it up, there's the elements of the vertices and the propagators. The propagators represent the motion from one point to another. All right, so let's talk about the propagators. The propagators from one space-time point to another, we can just draw them as lines in between. Of course, the particle doesn't really move along a straight line. That's not the implication here. The particle is a quantum mechanical particle. But the motion from one point to another, or the emission from one point, the detection at another point, we'll call a propagator, and we'll just indicate it by a line going from one point to another. Now I'm going to tell you what the meaning of the propagator is, the mathematical meaning of the propagator. The mathematical meaning of the propagator is just the amplitude that if you start a particle at one point, that if you create a particle at one point, that you'll detect it at another point. But mathematically what it corresponds to is to starting with a vacuum, applying the field operator, phi at, let's call it x, let's call this point x, and let's call this point y. These are not the x and y coordinates of a point. These are point x and point y. Right? So you've created a particle at x, and now you want to remove the particle at y, so that might be some phi of y. The creation operator creates the creation operator that's in phi of x creates a particle, and you can think of it two ways. You can think of, let's think of it this way. The action of phi of y on the bra vector 0 creates a particle at y. The action of phi of x here creates a particle at 0, but this can be read, create a particle at x, what's the amplitude that after a certain amount of time goes by that you find a particle at y. That's the meaning of this symbol here, the amplitude that if you created a particle at x, you would detect it at y. And that's what the propagator is. That is what the propagator is. It's just the amplitude that if you create a particle at x, you'll detect it at y. But now I can ask, what are the dimensions of this object here? What are the dimensions of this object? The vacuum, that's just a state, the state of lowest energy. Vacuums and states don't have dimensions. You wouldn't say the state has a certain mass. No, the state is just a specification of a configuration. It has no dimensions, but phi has dimensions. Phi has dimensions of inverse length. So what's the dimension of this object? Inverse length squared. Now, if there is no mass for phi, then there is no length scale in the problem other than just the distance between x and y. X and y would be the only thing which would specify any length scale in the problem. So can you guess what the answer to this quantity has to be? 1 over length squared, but what length? Right. I don't think it would make sense to put here 1 over x squared. Nah, that doesn't look good. How about 1 over y squared? Now, how about 1 over xy? I don't know, what do I even mean by xy? X is a 4 vector and y is a 4 vector. What do I even mean by that? All right. The obvious thing is 1 over the distance between them, x minus y squared, and the distance now meaning the Lorentz invariant distance, the proper time or the proper separation between them, 1 over x minus y squared. Right. So that's something we learned from dimensional analysis, that if there is no mass in the problem, if the particle doesn't have a mass, then the propagator is just 1 over the distance between the points squared. Notice something important. It blows up. It gets very big when the distance between the 2 points is close. So the amplitude for starting at 1 point and detecting a particle at a very close point, just on dimensional grounds, blows up and it diverges. That's the source of all divergences in quantum field theory, that propagators have divergences like this. And that can cause infinities in problems, just the fact that the propagator becomes so big at small distances. Okay. Everything else is just building up Feynman diagrams and calculating them. Right? But also, of course, interpreting them. Okay, so let's now start with the idea of renormalization and how it works in this very simple context. Let's start with renormalization of the mass. Now notice that in scalar field theory, the parameter that appears is actually the mass squared. It turns out that the mass rarely appears in scalar field theory. It only appears by virtue of taking the square root of the mass squared. The thing which appears in the dynamics of the theory is typically the square of the mass. Has to do with the fact that energy is the square root of p squared plus m squared. It's always m squared which appears. So we might as well ask about renormalization of m squared. What does it mean and how do we do it? So from this picture over here, we see that the interpretation of a mass term is just a basic simple Feynman diagram or a simple vertex in a Feynman diagram where a particle is absorbed at a point and emitted from the same point. Now, does it have to be exactly the same point? Well, if we have a microscope which is only good up to, we've built accelerators which study things down to a distance scale of 10 to the minus whatever it is, 17th centimeters or whatever it is, we're not really interested in the details of what goes on distances smaller than that. So if we can find a process in nature which would mimic this vertex, even if that vertex might be separated and fuzzy over a very, very tiny mass length scale, we might not be interested in that. If we're blurring our eyes to such fine distinctions, any diagram which absorbs a particle and re-emits it from a nearby point would be counted as part of the mass term in an effective description in which we don't look too closely. In other words, in a description where we get rid of all the very short distance and high frequency degrees of freedom. So let's ask, are there any Feynman diagrams that we can build that will mimic just a particle coming in and a particle going out? All right, so I'll give you one. First of all, let's build it out of this vertex over here, the phi to the 4th vertex, the lambda vertex. Here's a very simple process. A particle comes in, goes out, but here's a Feynman diagram where this is a little bit crazy, but still it's a Feynman diagram where a particle is emitted and comes back to essentially exactly the same point. Okay? Comes back to exactly the same point. Really what's happening is the particle is not going anywhere, of course. It's just being emitted and absorbed very quickly. That's the way to think about it. This is a Feynman diagram, and if I want to calculate it, I'm going to show you how to use the rules for calculating it. It's the amplitude for a process in which a particle comes in and goes back out. And this whole apparatus here may be on such a small scale that we might not even see it. It might be too small a scale for us to be interested in. But what is this propagator? This propagator is, where did I write the propagators? Did I erase them already? No, here it is. It's just 1 over x minus y squared. But x and y are the same point in this problem. Well, maybe they're not exactly the same point. Maybe I'm sort of blurring distinctions down to some what's called a cutoff scale, down to some very, very small distance scale. We might want to ignore separations on that small scale. That's called the cutoff in a quantum field theory. Cutoff, meaning to say we don't think about scales smaller than that. It's a sort of arbitrary thing to do, but we can do it. Let's say we're not going to be interested in distinctions on scales smaller than scale delta. All right. Then what should we put in here? We should put in a propagator which is separated by distances no longer than delta. We should put in a propagator which is separated by distance delta. If we're interested on length, if we're interested in physics on length scales a little bit longer than delta, but we are not interested on length scales smaller than delta, then we might want to say, let's calculate the Feynman diagram, but smearing this vertex here, smearing it, make it a little bit smeary in space-time, smearing it over a distance of size delta. Then what will we get? We'll get 1 over delta squared for the propagator. One over delta squared for the propagator. We're throwing away all scales smaller than delta. And what did I leave out? I left out the coefficient lambda coming from the 5/4 term. Lambda over delta squared. So what's the amplitude then in this approximation for a particle to come in, be absorbed, and be re-emitted? Well, it's got 2 terms. It has the original mass term. It can happen in 2 ways. It can happen just by the original mass term absorbing it and re-emitting it. And then it can happen by this more complicated process. And the total amplitude then is the original mass term. Let's give it a new name. I'm going to give it a new name over here. I'm going to call it m sub 0. 0 standing for original starting value. M sub 0 squared over 2 plus this over here. Another way to say it is if you're not going to look at distinctions on such small scales, that the effective mass term, the effective mass and the effective mass term is m naught squared over 2 plus lambda over delta squared. So this is an example of the renormalization of mass. It's getting rid of all degrees of freedom on scales too small to be interesting to us, too fast to be interesting to us, and lumping the two together. Lumping the two together into a single blurry effect, which we'll just make a blurry cross here. Stuff comes in and goes out. And the amplitude, the quantum mechanical amplitude for it, is m naught squared plus lambda over delta squared. All right, that's mass renormalization. Are there other, in other words, the true mass of the particle, the mass that you would see in the laboratory for experiments in which nothing moves so rapidly and so fast that you can see, where your accelerator simply doesn't expose distances smaller than delta, the effective mass that you see is this. Yeah, m naught squared over. Well, yeah, all right, this is the effective mass term in the Lagrangian, the effective mass, and of course the lambda over delta squared here, there's pi's and other things in there. There are numerical things in there. So it's not just dimensional analysis. Dimensional analysis plus evaluation of some integrals. But most of it can be done by much of it can be done by dimensional analysis. Okay, so this is the shift in the mass due to getting rid of very, very high frequency fluctuations and summing them up and putting them into an effective description. Change in mass, this would be called the renormalized mass. But of course, we're not finished. We haven't evaluated every possible Feynman diagram that can go into this. Let's do another Feynman diagram for the same thing, just to see how it works. All right, let's see. I'll put it over here. This is a Feynman diagram that looks like this. Again, it's using this. This is separated over here. Separate this over here. Here's another Feynman diagram. Let's evaluate it. It also has a particle coming in and a particle going out. But now we have something new. We have 2 points. What do we do with those 2 points? What do we do with those 2 points in order to get rid of things on scales smaller than delta? Well, we basically evaluate that diagram when the distance between these 2 points is again about delta. Strictly speaking, you might integrate over the position of these points. Let's even do that. Let's even think about that. In fact, we should think about that. Let's hold this point fixed. This is the point where the first particle is absorbed, and the second particle is absorbed or emitted from a nearby point. But remember that quantum mechanical amplitudes are always sums over all the possible ways that a thing can happen. So if we fix this point where the particle is absorbed, we should want to integrate or sum over all the places where it could be emitted, all the nearby places it could be emitted from. So let's see what that would give us. All right, I think we know that the propagator is 1 over x minus y squared. What's that?
The little bar across the circle would be 3 particles.
Yeah, 3 particles. That one? Yeah. We're still examining the effects of this term. This term has 4 particles coming together at a vertex. So here's 4 particles coming together at a vertex, and here's 4 particles coming together at a vertex again. Good. This diagram is higher order in lambda. It's to the next order in lambda. This one only has 1 lambda. Let's move this over here. Lambda over delta squared. That's what this one gives. Now we look at this one over here. This one will contain 2 factors of lambda. If lambda happens to be a small number, you might say this one is smaller. If lambda is small, then lambda squared is smaller. But let's work it out. And this will typically be true if lambda is a small number. But let's see what kind of things we get. First of all, we're going to get lambda squared. So this is a higher order Feynman diagram. Right? It's a second order Feynman diagram instead of a first order Feynman diagram. Contains the coupling constant or the constant lambda quadratically. And then it contains 3 propagators going between these 2 points. Right? Let's call the point of absorption here x, and let's call the point where the emission takes place, let's call it x plus delta. I don't just want to call it y, I want to call it x plus delta to indicate that there's a separation delta between the 2 points. Right? So what do we have? We have 3 propagators between these 2 points. What are those 3 propagators? Each propagator is a 1 over delta squared. Right? The distance between these 2 points is delta. The propagator is 1 over delta squared. So this means 1 over delta to the 6th. 1 over delta to the 6th. But now I'm not finished. Where does this, if the particle is emitted at x, it can be emitted at x plus, it could be, if it's absorbed at x, it can be emitted at x plus delta. But we're really interested in the amplitude integrated over delta. All possible ways that this event can happen, particle being absorbed at x and being emitted from any nearby position. Any nearby position where we're not going to look too closely about whether this position is the same or not. The right thing to do is to integrate this. Now I know I'm throwing rules at you, but you can imagine that these rules make sense. Quantum mechanical amplitudes are always sums over all the possible ways of going from one place to another. All the possible ways of getting from the initial particle to the final particle. Having been absorbed at x, you can be emitted at any point x plus delta, but then you have to integrate over delta. All right. What is the integral over delta? How many dimensional integral is it? Delta is a 4 vector. Did it give you a hint? We have 1 over delta to the 6th, but now we have to integrate over delta. But what does an integral over delta mean? It means an integral over the 4 coordinates, the 4 space-time coordinates of delta, right? You have to delta is a 4 vector. If you want to integrate over a 4 vector, you have to integrate over its 4 components. So we can write this d delta naught, d delta x, d delta 1, d delta 2, d delta 3, and so forth. Or we can just write d fourth delta. That means that it's an integral over delta, over the 4 components of delta. Okay, now where are we going to integrate it between? Well, we might want to integrate it to large distances, but it's not going to matter because this is going to be so concentrated at small distances that it's mainly dominated by when these two points are close to each other. So, good. So the important thing to know is that the integral goes from small distances of order delta to larger distances. From small distances of order delta to, so at the lower end of integration here, delta, for each one of the coordinates. Now, you care to guess how big this integral is? Lambda is a dimensionless number. It comes on the outside of the integral. Lambda squared. Put it over here. But how can I evaluate this integral? D fourth lambda over lambda to the 6th. Lambda to the 6th means lambda squared cubed. The answer is dimensional analysis. We are not going to do any integrals in this class. We're just going to say dimensional analysis tells us the answer to this integral. What does the integral depend on? Just on the lower end of integration here. That's all. That we don't take into account distances smaller than the cutoff. That's all it means. There's a cutoff in the field theory. And we cut off the distance scales at distance delta. The answer to this integral can only depend on delta. There's nothing else for it to depend on. So what's the answer got to be? 1 over delta squared. That's all it can be. So notice what we get from here. We get something that looks very much, of course there's a number here. You have to sit down and calculate more carefully. There's pi's and other things. So there's some numerical factor here. But the numerical factor is not terribly interesting to us. I mean, if we were trying to do a high precision experiment, it would be. But what do we find for this here? This here is the same as this, except with a lambda squared. Lambda squared over delta squared. There are many, many other diagrams which will also contribute 1 over delta squared with higher powers of lambda. For example, here's another diagram. Whoops. That one will also give, but how many powers of lambda? 1, 2, 3, 4. This will give a lambda to the 4th. Of some kind. There's others. There's lambda cubes also. So the answer is that there's an infinite series of terms, each with 1 over delta squared. Each with 1 over delta squared, plus a few other things. For example, we haven't used this term here. Let's see what we would get from this term, from the phi cubed. How do we make a diagram? Okay, this is interesting, a little more subtle dimensional analysis. What do we get if we have an integral that looks like this? An integral from delta to infinity of something which goes at small distances like 1 over delta. Let's say a one-dimensional integral now. One-dimensional integral d delta. What does that look like? That's a logarithm, right? That's a logarithmic integral. Now, on dimensional grounds, you would look at this and say this has no dimensions at all. So you might think that it's a constant. But it's not a constant because it's actually a divergent integral. Whenever you find a divergent integral, you have to be a little more careful. And an integral like this, you'll just recognize as a logarithm, and the answer will be logarithm of delta. So whenever you get an integral which has as many powers in the numerator as it has in the denominator, it's always a logarithm. That's a rule. We're not going to use it very much, but it's an interesting rule. In dimensional analysis, an integral with as many powers in the numerator as in the denominator always becomes a logarithm. If there's more powers in the denominator, then you just use dimensional analysis. You would say that this one, this would just be 1 over delta. Okay, so let's do this diagram here. This doesn't have a line running down the middle, and it's composed out of 2 cubic vertices. 2 cubic vertices with 3 particles coming into each vertex there. So what is this one going to be? All right, there are 2 propagators. That's a 1 over delta to the 4th. Each propagator is a 1 over delta squared. We have to integrate it. And what about the vertices? Each vertex is a g. So there's g squared. d4th delta. Again, we have to integrate over all the positions of this point, keeping this point fixed. The particle is absorbed here, emitted from some nearby point, but we have to take into account that that nearby point could be smeared over some range of locations. How about this? What do we get for this? Here we have as many powers in the numerator as in the denominator. Right? Log. And again, we integrate from delta to whatever. This one gives us g squared logarithm of delta. So we see there are times that we don't get 1 over delta squared. Sometimes we get logarithm, other possibilities also. But the single biggest thing, what do I mean by big? When delta is small, when the cutoff distance is small, which is bigger, 1 over delta squared or log delta? Logarithm is a very wimpy function. It doesn't vary very much. Logarithm is much weaker than any power. 1 over delta squared, when delta is small, is very dominant over the logarithm of delta here. Nevertheless, there are these logarithmic corrections to the mass, but the dominant things, when the cutoff gets small, if you have a very small distance cutoff, is these powers, these inverse powers of 1 over delta squared. All right, so this is called mass renormalization. Yeah.
Just a quick question. Log pick a new base?
Yeah, well, yeah, that is a good question, of course. And that's because I didn't tell you exactly how to calculate it. Let's just say log to the base e. Okay. But the point is, if you change the base of the logarithm, what happens to a log if you change the base? Not an additive constant, a numerical multiplicative constant. But I didn't tell you what the multiplicative factors here, the pi's and all that stuff are anyway. So that would be absorbed into the multiplicative factor here. So in a typical calculation, there will be some pi's and e's and other stuff here. And by changing the base of the logarithm, you'll just change these coefficients here. So it doesn't...
Or your units of length or something like that.
No, these are dimensionless. These are completely dimensionless. So it just changed the numerical coefficient.
E was units of mass.
Oh, in this case, you're right. Yeah. For this case, yes. Yeah. Right. The point is, yeah, the g's have units of mass, but what are they supposed to be giving? They're supposed to be giving a correction to something which is a mass squared. So the units of this g squared here is the same as the units of this mass squared. That means the rest of it is dimensionless.
Well, all I was saying was that you could absorb which logarithm it is into your length scale.
You can, but you can also just notice that this and this have the same units, and say, look, there's a numerical number here that has to be computed by somebody with a little more power than we're exhibiting here. But you're right, it can be absorbed into units. Okay, that's the idea of mass renormalization, yeah.
This gives an amplitude, and amplitude squared is the probability of this happening.
It is. But more important, this kind of amplitude represents the mass of a particle. It's more important for our purposes now that a diagram in which a particle is absorbed in a location and emitted very nearby is an effective description of the mass of the particle. Now, of course, it's not obvious how this translates into the inertia of a particle and so forth. For our purposes now, it's just a parameter in a Lagrangian, but we're seeing that the renormalized parameter, the parameter after you get rid of distances smaller than a certain length scale, the corrections to it, here they are. Well, it's not just the mass that gets renormalized. Let's do another example.
Well, even if you just have the mass renormalization, you still have an infinite number of terms, don't you?
An infinite number of what?
A lot of those diagrams,
Yeah.
so I mean, you can keep going,
Oh, yes. Yeah, let's keep going.
right? So it's already infinite.
Now, if lambda is small, it may be that the series is a series of smaller and smaller terms, and it might converge. But still, there are an infinite number of terms, and
Yeah.
yeah,
Right, depends on, yeah, what happens to lambda, right?
yeah, right. Let's talk about the renormalization of lambda. Lambda is also something that gets renormalized, so let's talk about that. It's not just the mass that gets renormalized. Every term in the Lagrangian can also get renormalized. Let's see how that works.
The delta has the units of length, right?
Big delta has units of length, yeah, so does small delta.
So when you do log of it, then you get really weird things, because the log has all sorts of powers.
I have all sorts of what?
All sorts of powers when you do the expansion of
A
log.
log is counted as dimensionless because really a log always means log of delta over some other scale in the problem. And I didn't want to get into that. The logs are confusing. The real things that I'm interested in are these things. And these are less confusing. These are dimensionally just what you'd expect. I'm sorry I told you about logs. Often what happens is the logarithm is really log of delta times some energy scale in the problem that you're interested in. But let's get rid of logs. Logs
Actually,
are
you meant lowercase delta in that case, right?
lowercase delta what?
Oh, you were using,
Have I mixed up lowercase delta and uppercase delta?
yeah, capital delta was the inside the integral.
Oh yeah, yeah. And the answer should involve small delta. Right, sorry. Good. The answer always involves small delta. Big delta is an integration variable. All right, let's take another example. From an operational point of view, meaning an experimental point of view, lambda phi to the fourth is nothing but the amplitude for a particle, for two particles to come in and to go out again as two particles. And from an operational experimental point of view, if all of this takes place again on a scale which is too small to see, you lump it all up into an effective coefficient of phi to the fourth. Two particles in, two particles out, phi to the fourth. All right, so for example, you could have Feynman diagrams which look like this. This will also contribute a renormalization to phi to the fourth. I'm not going to work it out. The reason I'm not going to work it out is because I know it'll give a log, and I don't want to tell you any more about logs. It will give you a log. But each one of these terms here is something which in itself can be renormalized. So what's going on is the effect of very small distance physics. When you sum it all up and take it all into account, the same way we took the electrons into account when we studied molecules, for example, we take them into account, we solve for them, we get rid of them, we do whatever has to be done, and we find some effective description which doesn't involve those microscopic degrees of freedom. The result is renormalization of everything. Everything gets changed, everything gets shifted. So the parameters of the theory that you measure are not the parameters of the theory that you input into the theory. That's the main lesson. Parameters of the theory you measure are those which take into account all the short distance physics on scales smaller than you can see.
Would you repeat that again? What you measure includes the scale smaller than what you see or not what you see?
Yeah, what you measure has taken into account by summing all the Feynman diagrams involving length scales smaller than what you can see. It has an effective output, which is the sum of all that stuff, which you lump together. You lump it together into a single thing that you call the mass squared over 2. So the physical mass squared, the thing you measure when you do an experiment at, let's say, relatively low energy that doesn't involve really, really small distances, is this renormalized mass here, which is the sum of all that junk.
So is the conclusion that somehow or another the M0 term must be cancel all of those other terms?
Exactly. Yeah, we're going to come to that shortly. But before we do, let's talk about the renormalization of some other masses. This is the renormalization of the mass of a scalar particle. You might think it works essentially the same way for a fermion, and it doesn't. Fermions are better behaved. I would call this bad behavior. You want bad behavior in the following sense. You wanted to get out an answer. Imagine in your head that the cutoff distance scale is something very, very small. Imagine in your head that the cutoff distance scale might be the Planck scale. We might be trying to account for all physics on scales between the experimental scale all the ways down to the Planck scale, all the ways down to that very, very small Planck scale. Then what we would put in for delta here would be the Planck length. The Planck length is terribly small. It's 19 orders of magnitude smaller than the size, 20 orders of magnitude smaller than the size of a proton, 17 orders of magnitude smaller than the most current up-to-date accelerator experiments, 17, maybe 16 orders of magnitude. And so delta squared is a very, very small number in ordinary particle physics units. For example, if we use GeV, then the Planck distance would be 10 to the minus 19th inverse GeVs. And 1 over delta squared would be what? 10 to the 38th 10 to the 38th, but what kind of answer do we want to get, for example, for the Higgs boson? The Higgs boson is an example of a scalar particle. What kind of answer do we want to get? We want to get something like about 200 GeV. 200. But what are we getting? We're getting 10 to the 38th. This is terrible. We don't want to get 10 to the 38th. The only way to avoid it, incidentally, the signs of all of these things, some of them may be plus, some of them may be minus. I didn't track the signs of anything. And m0 squared itself can be negative or positive. We want to get out a certain answer which is of order 200 GeV, but we're getting contributions which are 17 orders of magnitude bigger. The only way that this can make sense is if all of this cancels precisely to 17 digits. Okay, to 17 digits, this has to cancel and leave over something in the it has to cancel, not the 17, 17 to 34 digits, and leave over something, I think it's in the 35th, or maybe it's in the 34th digit. This is called fine-tuning. This is the fine-tuning problem of the Higgs boson. Let's just recall what we know about the mass term of the Higgs boson, and where we know it from. The Higgs boson has a potential, or the Higgs field has a potential which looks like that. Near the origin, it looks like phi squared all right, but with a negative coefficient. I never told you that this m0 squared was positive. It can be negative or positive. Yeah?
Is lambda less or greater than 1?
lambda is assumed to be a number which is not much bigger than 1. Now, why do we assume that? We assume that, first of all, because this would all be nonsense if the terms, completely intractable if the numbers got bigger and bigger and bigger. But even more than that, we know that this kind of quantum field theory becomes mathematically inconsistent when lambda gets big. So lambda of order 1 is as big as it could be, and it really should be smaller than that. So assume that lambda is modestly small. Okay. Now, let's modestly small, but not humongously small. There's no reason for it to be very small. And in fact, experimentally, we know that it can't be too small. Okay? We know that it can't be too small. We know it's a number of order 1%.
Even if it's less than 1, there's still a lot of terms that are in there just because of the deltas.
Well, if lambda itself was 10 to the minus 38, we might not worry
No,
about it.
if it's, 0.9, then, it falls
Right.
off, but it still has
Right.
a number of terms that you have to.
Oh, there's an infinite number of terms, and all, you have to go a long way down this chain before lambda to the high power over delta is a relatively small number. So it means that a whole bunch of them have to conspire. I'm not sure, maybe 50 or something have to conspire to give this ridiculously small answer. Small. Lambda? Yeah. Lambda is typically a number of order 1%, yeah, right. Let me just remind you what we know about lambda. We speculated, or I will tell you that there's good reasons, we won't go into them, why the potential for the Higgs boson, first of all, why it has to have this Mexican hat shape. That was in order to facilitate the problem of getting masses, spontaneous symmetry breaking, and so forth. But the typical potential would be of the form minus, let's call it mu squared over 2 phi squared. I've called it, instead of calling it m naught squared, I've called it minus mu squared because it's got to be negative. We know that it has to be negative to get spontaneous symmetry breakings. Plus, again, lambda phi to the 4th. And there might be more terms there, but the other terms are believed not to be important. All right. Where does the minimum occur? The minimum occurs, we can calculate the minimum by differentiating with respect to phi and setting the derivative equal to 0. And what you'll find is that at the minimum, phi min squared, which we also called f squared. Remember, we call this distance here f. We also call that f squared. That was equal to mu squared over lambda. If lambda is a number of order of magnitude 1 and so forth, and f, do you remember about f? How big did f have to be? For experimental reasons. Remember, all the masses of the Z and the W boson are all controlled by F. The known masses of the Z boson told us that F was about 200 GeV. All right? That tells us that unless lambda is some absurdly different number than 1, which it shouldn't be, that mu is also a number which is of order 200 GeV. In other words, this mass term is of order 200 GeV, even if it's negative. The hell with the fact that it's negative. It's of order 200 GeV, but yet it is composed out of this ridiculous sum of terms, every one of which is 38 orders of magnitude, which can be as big as 38 orders of magnitude bigger than the thing you're trying to get. This is known as the fine-tuning problem. Sometimes it's called the gauge hierarchy problem, the hierarchy problem, the hierarchy being the hierarchy of mass scales from the Planck scale down to the scale of ordinary particle physics. Enormous gap or enormous ratio of scales. And it's not just that there's a small number in physics, the mass scale of light particles. There's this incredibly finely tuned thing which is composed of many pieces, all of which have to add up to something small. So that's ridiculous. I mean, we've understood that that's a ridiculous idea for, I don't know, sometime in the early 80s or late 70s when this problem was first identified. And the question is, what do you do about it? But before I get onto that, let me talk about the mass renormalization of other particles, the other particles of the Standard Model, and why they are not in themselves a problem. It's really just one fine-tuning. You don't have to separately fine-tune the mass of the electron and those sorts of things. Why doesn't the electron have the same kind of problem? Okay, so let's talk about fermions. Fermions don't have the same sort of problem. So let's talk about the mass term of a fermion. The mass term of a fermion involves the mass, not the mass squared, and it's contained in the term in the Lagrangian, which is m psi bar psi. Psi are the fermion fields that describe the creation and annihilation of fermions. And the term in the Lagrangian that controls or that defines the mass of the electron or the quark or whatever it is just has the form m psi bar psi. Now, as I told you last time, or several times ago, first of all, psi bar psi is also a term in Lagrangian which creates a process where a fermion comes in and gets re-emitted. Psi absorbs a fermion at a position, and psi bar emits it. So again, it's very, very much like this term here, except it only involves the mass and not the mass squared. But that's not a big deal. We can certainly imagine diagrams which renormalize the mass. But I'm going to show you now why it's not as big a deal for the fermions. So do you remember I told you a couple of times ago that psi bar psi is a thing which always absorbs a left-handed particle and emits a right-handed particle, or absorbs a right-handed particle and emits a left-handed particle. It flips you between handedness of the fermion. If the fermion is moving down and the psi bar is an axis with a right-handed helicity, a right-handed spin relative to its direction of motion, then the mass term will flip it. Okay? That's an important thing to know. So this is a thing which takes left to right or right to left. Now, what kind of thing could renormalize the mass of the electron? For example, one of the things that we put into the Standard Model was the emission by the fermions of a scalar, or the emission of a gauge boson. Emission of a scalar, or the scalar, let's represent this way. The scalar is a dotted line, the gauge boson. This could be quantum electrodynamics. In quantum electrodynamics, the only thing that can happen to an electron is it emits a gauge boson, the photon. What happens to the handedness of an electron when it emits a gauge boson? The answer is nothing. The handedness doesn't change. So emitting a gauge boson takes left to left or right to right. You can work that out from the properties of the Lagrangian, that the emission of a photon doesn't flip the helicity of a fermion. What about the emission of a scalar particle? Well, it turns out the scalar particle does flip from left to right or from right to left. So gauge bosons don't flip. Scalar particles do flip the direction of rotation of the spin of the electron relative to its momentum. Okay, now let's look at processes which could renormalize the mass of the electron. And this is fun. This is a little bit of a surprise. Supposing the electron starts out with no mass. Notice in the boson case, where is it? That even if the particle started with no mass, it gets this huge, humongous contribution from renormalization. And the renormalized mass is not dependent. The renormalization of the mass is not dependent on whether the electron had, or whether the particle had the mass in the first place. Just all these terms would be there, even if this one weren't there. Now let's take the case of the electron. So what kind of things can we have? Here's the electron moving along. It could emit and absorb a photon. Now, by definition, a mass term, practically by definition, a mass term is recognized as an amplitude for left to become right, or right to become left. From an experimental point of view, a mass term was recognized as an oscillation between left and right. Can we get left going to right? Can that happen? And let's suppose the starting mass of the electron is 0. Let's begin with the electron mass being 0. Is there any way to go from left to right? Well, you could emit a photon and reabsorb a photon, but a photon always takes left to left or right to right, and there's no way by a sequence of emissions and absorptions of photons to make a left go to right. The conclusion is, in quantum electrodynamics or in any theory which only involves the emission of gauge bosons, fermions get no mass renormalization at all. They get no mass renormalization at all. So the electromagnetic self-energy of an electron, if the electron started massless, the correction would be 0. A massless electron is a consistent thing, well, in pure quantum electrodynamics, not in the standard model, but in pure quantum electrodynamics, a massless electron is a consistent thing, and if it starts out massless, the bare, or the starting point, the input mass, it will stay that way. Why? Because photons emitted and reabsorbed will not flip from left to right. What about, supposing now there is a scalar particle that the electron couples to? The Higgs field is an example. Let's suppose that the Higgs field can be absorbed and re-emitted, or sorry, emitted and reabsorbed. Right? What kind of thing does that make? Can that make left go to right? No, it can't, because the scalar emission here always takes left, where is it? Always takes left to right, or right to left. This is the scalar particle here. The scalar particle always involves a transition. And so here you can go from left to right, all right, but then in the reabsorption here, you're going to go back to left. And if you think about it, no matter how complicated the Feynman diagram is, it's always going to involve an even number of vertices, and because it involves an even number of, whatever gets emitted must get reabsorbed. That's all it comes down to. If it's going to be just electron goes to electron, whatever gets emitted must get reabsorbed, the number of vertices must be even, and if the number of vertices is even from this, then you can't make left go to right. And so again, scalar emission and absorption will have no effect on the mass of the electron if it starts from 0. Okay, can you ever get a shift of the mass of the electron, for example, in quantum electrodynamics? And the answer is yes, but only if you start with a mass. What does a mass do? A mass can be thought of as a vertex in a Feynman diagram, which does take left to right. But the coefficient is proportional to the input mass. So let me draw a Feynman diagram which does shift the mass of the electron. All you have to do is emit and absorb a photon. But in the middle here, have one of these mass insertions, which itself flips from left to right. Then you can start with left. Emitting the photon takes you to right, but then the mass term takes you back to left, and then, oh, sorry, I didn't do that right. Left goes to left, and then the mass term takes left to right, and then right to right. The value of this Feynman diagram contains two factors, or three factors. It contains the electric charge twice. Remember, the Feynman diagram for the emission of a photon is proportional to the electric charge. The coupling constant is the electric charge. So this kind of Feynman diagram would have the electric charge squared, but it also has the original starting mass. Original starting mass. Let's call it m naught. So we see that the shift in the mass is proportional to the mass itself. So now we can write down that the mass of the electron will consist of m naught plus something of order e squared times m naught plus, more complicated diagrams, e to the fourth times m naught, in such a way that if the starting mass was 0 to begin with, it would remain 0. The implication of that is that not if the starting mass was 0 that it would remain 0, it's that if the starting mass was very small, it would remain small. You would still ask the question, why is the electron so light compared to some fundamental scale? But at least you wouldn't have this fine-tuning problem. You would not be canceling out differences between large numbers to make a small number. You say, for reasons I don't know, the mass of the electron may be small, and all the corrections to it are even smaller. So fermions are, in that sense, better behaved than scalar particles. What about gauge bosons? Well, gauge bosons have the same property, that if they start out massless, I won't go into it, if they start out massless, they remain massless to all orders. So what that means is that to understand the mass scales of the standard model, the fine-tuning problem is really only one fine-tuning problem. It's the fine-tuning that's associated with the Higgs boson. If you get that one right, all the other ones will be okay, because all the other masses are direct responses to the shift of the Higgs field. Where is it? I don't know. We erased it, I guess. Yeah, to the shift of the Higgs field. And if the shift of the Higgs field is controlled, and if it doesn't undergo this enormous renormalization and shift off to some huge amount, then everything else will be okay. There will be no other fine-tunings. The only fine-tuning in the standard model, no, really crazy fine-tuning, the only really crazy fine-tuning is the mass term from the Higgs boson, which has to be about 38 orders of magnitude smaller than whatever fundamental scale you might envision. That's the great puzzle that supersymmetry and other kinds of theories like that are intended to address. Roughly speaking, the question is there any kind of context where the Higgs boson cannot get a mass correction which is enormously large? Is there any kind of theory where the Higgs boson itself will also be a particle whose mass isn't driven to enormously large values by renormalization? And so the answer is yes, we know some. There's one other fine-tuning, extreme fine-tuning in physics. It only comes into play, though, when you start thinking about gravity. Before you think about gravity, if you don't think about gravity, then it's not a problem. It is a problem that's associated with renormalization. And it's the problem of the renormalization of vacuum energy. Renormalization of vacuum energy is also a serious problem. It's also a thing of very serious need for fine-tuning. And I'll just tell you what it is since we're dealing with fine-tuning. First of all, what the energy of the vacuum is, for most purposes in physics, doesn't matter. Why not? Well, it's an additive constant to all energies. If empty space has energy, so be it, but then as long as when you add a particle, it adds the right amount of energy, that's okay. Who cares what the vacuum energy is? It doesn't play any role in physics. The real point is that only energy differences are important in physics. Energy differences. So when you think about the mass of the electron, don't think about it as the energy of electron. Think about it as the extra energy that you have to add to the vacuum. Whatever the vacuum energy is, you have to add a little energy when you add an electron. So it's energy differences, the energy difference between the energy of an electron and the energy of a vacuum, which is really what we call the mass of the electron. So who cares then if the vacuum gets its energy shifted by a large amount as long as everything else gets shifted along with it. All right, so we'll come back to who cares in a minute, but let's just ask what does happen to the vacuum energy. And the vacuum energy is something which is also renormalized, and it's renormalized by diagrams which have no input and no output particles. In other words, just vacuum to vacuum. The effect of such diagrams is to renormalize the energy of the vacuum, but who cares? I mean, the vacuum energy is of no physical significance, but nevertheless, let's ask what it looks like. So for example, in the 5-4 theory, let's do the 5-4 theory. So there are, let's draw a diagram from the 5-4 theory that involves no in particles and no out particles, just vacuum to vacuum. Here it is. Four particles at the vertex here, and that's it. Right? How big is that diagram? Numerically, how big is it? Well, it contains lambda, and then it contains a propagator from here back to the same place. That's a factor of 1 over delta squared. It's a factor of 1 over delta squared if this little separation here is of order delta. But then there's another one here, which is another 1 over delta squared. So the whole thing is 1 over delta to the 4th. Every diagram that you can write down will typically go as 1 over delta to the 4th times, there are more complicated ones, but they'll also go as 1 over delta to the 4th. And so the vacuum energy is also something that gets renormalized. Because it gets renormalized, it means that if you really want it to be 0, you better fine-tune it to very high precision. But on the other hand, who cares what it is? We don't care what it is. We don't care what it is until gravity becomes important. And the reason is that in standard theory, the source of the gravitational field is energy. If the vacuum has energy, it means that the vacuum itself, empty space, gravitates. We're not going to go into this now. This, of course, has to do with dark energy. It has to do with the cosmological constant. We'll talk about it another time. But yes, this is also something that has to be fine-tuned. And it has to be fine-tuned, once again, to enormously high precision. So really, strictly speaking, there are 2 fine-tuning problems in physics, at least 2 that we know about. One of them is the vacuum energy, which has to be tuned to something like 123 decimal places, and the other is the Higgs mass, which only has to be tuned to something like 30 or 35 decimal places or something like that. These are the 2 problems. In many respects, these are the sort of biggest puzzles in particle physics at the present time. Of course, it may turn out that these puzzles are simply due to a misstatement of the problem. You know, it often happens that, that really, really thorny puzzles go away when you state the problem correctly. But it's been a long time since these problems were identified, and nobody really knows what the solution to them is. Supersymmetry is a potential solution to the fine-tuning of the Higgs boson. It is not a potential solution to the fine-tuning of the cosmological constant. So the next time, I'm getting a little tired, I think we'll quit early tonight. Time for a couple of questions, but the next time I'll start to tell you a little bit about what supersymmetry is. Mm-hmm?
It looked like when you had up the summation for the Higgs,
For the mass of the Higgs?
yeah,
Yeah.
that it would actually depend on delta. The delta was kind of arbitrary. You said Planck distance, but it could be 10 times the Planck distance. So
It could be 10 times the Planck distance.
So does the fine tuning depend
No.
on the delta? That doesn't make any sense.
We can talk about all the contributions to the mass of the particle which come from fluctuations of wavelengths from degrees of freedom down to some very small distance scale. The answer will depend on that scale. It will depend on that scale. So the real question is, ordinary quantum field theory, how far down in scale do we expect it to make sense before it becomes nonsense? All those modes, all those frequencies are real things that we think are really there because quantum field theory makes sense down to those scales. That's a sort of lower bound on what these effects are. What I'm saying is if we have some scale where we expect that physics will change, it could be the Planck scale, it could be some unification scale. If we have some idea where physics changes, then the physics down to that scale contributes some contribution, and it will only be bigger than that. That's the point. It will only be bigger. This is kind of a lower bound. Now, what do you choose for delta in practice? In practice, you choose for delta the distance down to which you think you understand physics at the present time. So we have the standard model. The standard model appears to make sense to very, very small distance scales. We talked a little bit about unification of coupling constants, didn't we? About how the coupling constants seem to track together, and they seem to come together at something like about 10 to the 16th GeV. Well, a lot of us think that that's the scale where quantum field theory continues down to. Beyond that 10 to the 16th GeV, for even smaller scales, it can only get worse. But if you believe that quantum field theory in the standard model makes sense to some small length scale, let's say 10 to the 16th GeV or whatever it is, then you're obligated to say where the effects of all the scales in between, what they did to the theory, how they renormalized the theory, and what canceled them all out. And it can only get worse by thinking about even smaller scales. So, right, so we think we have a pretty good understanding of physics down to scales which are many times smaller than the weak interaction scale, in this ordinary weak interaction scale. We have a good understanding of it only, though, if we can explain what happened to the mass contributions and the renormalization contributions from scales between the experimental scale and the smaller scale where we think the theory makes sense. So in that sense, what I've described is sort of the lower bound on how bad these things can be, where delta we simply take to be the scale at which we still believe the theory makes sense. Yeah.
What's the definition of a scalar particle, and can you give an example of a scalar particle?
Higgs particle
It is the scalar particle.
is a scalar particle. There's probably more of them. We've never actually detected an elementary particle that we would call a scalar particle.
How do you define a scalar particle?
How do you...
What is a scalar particle? How do you define it?
It has only
not a
one
boson,
component.
not a fermion.
It doesn't transform under rotation of coordinates. It doesn't transform under rotation. The photon is a vector particle. It's described by a vector potential, which when you rotate coordinates, the components of the vector change. The gravitational field is a tensor particle. Okay. Fermions, simply stated, let me say it even simpler. A scalar particle is a particle with spin 0. No angular momentum. No spin angular momentum. Right, that's the simplest statement of it.
The Z particle is a gauge boson as well?
Z particle is a spin 1 particle.
Oh, it's a spin 1 particle. Okay.
All gauge particles are spin 1.
W plus and W minus are spin 1s, and they're the same as the Z particle, that same
The
group?
spin is the same as the Z particle, which is the same as a photon. All right. All these particles called gauge bosons are very similar. I keep emphasizing they're very, very similar and parallel to the photon. They have a Maxwell-like description.
For the vacuum energy problem we discussed, how come the Bose ground state doesn't cancel the Fermion ground state?
Okay. Right. That would require, again, a huge amount of fine-tuning. The actual answers are a little more delicate. They involve various numbers here and so forth. There's infinitely many such terms, some of them positive, some of them negative. And some of the ones from fermions are negative, some of the ones from bosons are positive. But unless the masses of the particles and the coupling constants were very delicately matched, they wouldn't cancel. Right? Matching them is what supersymmetry does. Supersymmetry does exactly that. It cancels out the question was why fermions and bosons. Now, the questioner knows something. What the questioner knew is that at least the simplest Feynman diagrams for the vacuum energy of fermions is negative. The simplest corresponding diagrams for bosons is positive. And in principle, if a fermion and a boson had exactly the same mass, they could cancel each other in the vacuum energy. But if they have slightly different masses, then you're going to get, again, these quantities here with huge coefficients, which may be proportional to the mass difference, for example, of a fermion and a boson, but or different coupling constants. You would have to fine-tune it in any case to get it to work out. That's what supersymmetry sometimes does. Okay. If there are no other questions.
For more, please visit us at stanford.edu.